So good morning and welcome to my presentation today. It's on hybrid operation and digital twins for complex systems. I would like to discuss with you today some of the implications, what happens when we are combining deep learning algorithms with physics-based approaches. But before we start, I would actually like to first give you some definitions of how we understand digital twins and what do we use them for? Because there have been different definitions of digital twins, and somehow everyone who is using the term is understanding something a bit different. But in the context of today's presentation, I would like to define the digital twin as following. So this is for us a living model of the physical asset or system which continuously adapts to operational changes based on the collected data and information and can forecast the future of the corresponding physical counterpart. So there are different dimensions on how we can look into digital twin integration and which aspects are actually important for us. And particularly what is really relevant for us is the simulation capabilities. On the one hand, we would like to model the digital twins with multi-physical behavior. But on the other hand, what is really relevant for us is this look-ahead prescriptive simulation capabilities, so that we are not just simulating, but really are able to predict how the system conditions are going to evolve over time. We're also interested particularly in this multi-factory environment, and we want to look into the digital twins through the entire lifetime or through the entire life cycle. And for us, it's particularly relevant that they're also able to update in real time. So that's the different dimensions. And obviously, they're also relevant works done in other dimensions, but this is what is relevant for the task that we're trying to solve. So what are the tasks that we are trying to solve? And we are particularly interested in rare events. And rare events happen in complex systems, as already mentioned, quite rare and quite seldom. And typically when they happen, then the consequences may be quite high. So this is why we would like to detect them on time, but also to be able to act on them before they're happening. So that's why it's not only relevant to detect when something is happening, but also to be able to distinguish which of the events or which of the fault types are actually occurring. And ultimately, we would also like to predict what is actually the remaining useful life of a component, so when the component is going to fail. So beyond detection, we would not just like to detect when something is going wrong, but really to predict how the system condition is going to evolve over time. And in the course of today's presentation, I will be focusing particularly on these two parts, on the diagnostics and prognostics, because these are really the more complex behaviors that we need to model here. And as already mentioned in the title, we're interested in looking into hybrid approaches. And hybrid approaches is where we're trying to combine data-driven approaches with physics-based approaches. And on the one hand, we may have access to different degrees of underlying physics, so from no physics to lots of physics. And on the other hand, we can also have access to big data, but also to quite small data. And depending on which combinations we're actually facing in our problem with, we are then are able to combine either the different degrees of data availability or the different degrees of physics integrations. And we will be looking into somewhere around here where we have some data, but where we also have, well, actually some physics and partly quite a lot of physics. So if you would like to integrate bias into our models, there are again different ways of integrating that, or different types of inductive bias that we can integrate there. So on the one hand, we can have the learning bias, the inductive bias, or the observational bias. So for example, if we are integrating the structural inductive bias, we're trying to use the structure of our problems, or if our problem is represented through a network, we could, for example, use graph neural networks to use this information in our models. And what we will be particularly looking into is this observational bias, where we're using the information from the data that is coming in. If we would like to integrate different physics into our deep learning models, there are obviously different ways to do it, but also we can do it at different hierarchical levels. So for example, if we have quite a complex physical system model, and we have quite good understanding about several of the submodels, we can possibly model those for the physics that we are understanding, and substitute one of the modules, for example, to a deep learning model. We can also combine information from the physical model and use that as an input to the hybrid system model. So this will be particularly something that we'll be looking into. But we can also use physics-informed or physics-induced neural network, where we're using, for example, partial differential equation to help us with the learning process. We can also learn the underlying physical equations through data and then use them back into our models to improve the generalization ability. So there are different combinations, and I will be particularly looking into that one where we're combining observations with a physical system model, and then where we're training the model to predict our desired output. And that's the framework that I will be using for two different applications. So on the one hand, what we're assuming is that we have a physics-based physical performance model, and we have data from the real process. So we are then using the observations from the real process to calibrate our physics-based model, so to deduce the model parameters, and then we are using the model parameters and the observations from the real process as input to our deep neural network. So that's how we are assuming it, so that on the one hand, we have a well-calibrated physics-based performance model, and we are using the inferred parameters from this physics-based system model as input to our deep neural network, and that enables us to enlarge the input space and also to improve the learning capabilities. And just to distinguish between the different approaches, so what we are looking into here, or what we're interested in, are degradation models or degradation mechanism, and this is what we would actually like to model, because what our task is to predict when the system is going to fail. So obviously, if we are able to model the degradation mechanism, this would be our ideal input or ideal model for the type of problems that we are trying to solve. However, we typically don't have this either detailed modeling of the physics of failures or the macro level, the modeling of the physics of failure to have our cumulative damage models for fatigue, for example. So these are typically only available for rather simpler systems or to some dedicated mechanisms. However, what we will be particularly looking into these performance models, where we are not modeling explicitly the degradation mechanisms, but would rather to use the impact of this degradation mechanism on the model parameters, and then learn from that how the system condition is going to evolve over time. So that will be particularly in the focus of the talk today. So I would like to start with a case study on prognostics, where we were using this framework that I just outlined to predict the remaining useful life of complex systems. So the remaining useful life of a component is defined as the amount of time a component can be expected to continue operating within its stated specification. And when we look into the health index of a complex system, that at the beginning they start with all at about the same time, but then depending the same condition, but then depending on how they are operated and also depending on the system configuration, the remaining useful life can diverge quite a lot between the different components of a fleet or complex systems. And this is what we would like to distinguish or to predict which of the components will going to fail quite early here, or which can we still operate for longer period of time. As already indicated, the framework comprises for us, on one hand, the real process observations and measurements, and on the other hand, we assume that we have access to a system model. So we then calibrate the system model with the observations of our real process. And with that, we are then getting access not only to the real measurements of the process, but also to the virtual sensors. And the virtual sensors are measurements that we are not either not measuring or not able to measure in the real process, but that are only contained in our system model. And what we have on top is our calibration parameters. So these are our thetas here. And the thetas provide us quite informative view on the condition of the components, on the degradation condition of the components. If you only wanted to look into our problem in a purely data-driven way, we would only consider this input here. So this would be the purely data-driven approaches. And when we are looking into the hybrid approaches, we are taking this purely data-driven information that we have access to, and then we are adding on top this inferred physics-based parameters, on the one hand, the virtual sensors and the calibration parameters. And then we are feeding that into our deep learning model to predict the remaining useful life in this case. And we applied it to a case study of turbofan engines. We collaborated for that with NASA, and it was the commercial modular aero propulsion system simulation environment. So this is proprietary owned by NASA. And we were then able, on the one hand, to induce more informative or more realistic operating conditions, but also more realistic degradation conditions. So for that, we were also using the real flight conditions, and then we're also aggregating the impact of each of the flights on the system condition, how it degrades over time. And in this specific case study, we looked into a small fleet of 9 turbofan engines, where we split it into 6 training engines and 3 testing engines. And that's how a flight envelope may look like. And we had 2 different failure modes. On the one hand, it was the HPT degradation, and on the other hand, it was the HPT and the LPT flow and efficiency degradation. And then, so this the lifetime of all the different flights. So as we see, there are different flight conditions and different flight profiles, and the engines would be run until their end of life. So as mentioned, 6 engines were used to train the models, and 3 engines were used to test how the models actually generalized and if they were able to generalize to unseen conditions. So this is just the kernel density estimation of the different flight or of the different units. So the first 6 were our training units, and the unit 11, 14, and 15 were our testing units. And this is just to show you that actually the unit 14 was behaving was operated in a quite different way compared to all the training units. And even unit 15 was operated also slightly differently to those of the training units. So this was providing us a good environment to test how well the models would be able to generalize to unseen conditions or to unseen operational profiles. So as already mentioned, we would have our real observations, we would have our model, we would then calibrate the model, we use the unsentient Kalman filter to calibrate the model. But in fact, for this block here, we can use different approaches, and we also propose to use, for example, reinforcement learning for this calibration step. So then we were collecting all this information, feeding that in, and here you see the architecture of a convolutional neural network. However, you used also others, as you will just see in a minute, and we were training it to predict the remaining useful life. So how long can the system still remain operating under healthy conditions? And this is what was the result. On the one hand, we have now here the purely data-driven approach, and these are the feed-forward neural networks. And now we see here on the right the prediction accuracy of the hybrid approaches. What you see here are the different estimation during the flight envelope. And if you compare the purely data-driven and the hybrid approach, what you see on the one hand is that the variability during the flight has actually decreased, but then also what we see that the prediction actually converge much faster and then remain within this prediction horizon that we defined, or prediction accuracy that we defined of being between plus and minus 5 cycles. So as mentioned, we also applied the convolutional neural networks, and as you see, the convolutional neural networks improve the performance of the purely data-driven approaches already quite significantly, but then still there is quite a difference between the purely data-driven and the hybrid approaches here. And just to show you the numbers, so here are here is the performance of the feed-forward neural network, and we also applied or tested it on LSTM models, and we also applied convolutional neural networks. So the convolutional neural networks perform overall the best, and the hybrid version of the convolutional neural networks perform them even better. But as you see in all of the models, the hybrid approaches actually outperform the purely data-driven approaches. And this is a strong indicator that this information provides more insights onto the system condition and the health and how this health condition is evolving over time. We also wanted to evaluate when can we actually be sure about the end of life of our system. And in this case, we only looked into the CNNs because this was the best performing model for us. And as already mentioned, we defined this error bound of being 5 cycles. And what you see here is when is the prediction within this 5 cycles until the end of life of this component. And these are the different cycles for the data-driven and the hybrid approaches. And as you see here, for the hybrid approaches, we were able to improve this prediction horizon by around 130%. And for some, it was even about 200%. And for the unit 15, we were still able to improve it by 50%, but not as much as for the other units. What we also wanted to test was how do our models perform if we reduce the training data size? Because this is usually the promise of the hybrid approaches that if we introduce additional physics-based information, that we probably need less data to train our models. So what we then did was that out of this 6 training units, we just took this 16, 18, and 20 as our training units, but then we left the testing units as being the same as for what we had before. And this is the performance, what you saw before. And now what you see here is the comparison of the CNN trained just on this 3 training units that we took out of this entire fleet of the 6 units. And what you see is that the performance actually remained more or less the same depending on which indicator you take. So this is a typical score that was used also on the previous data sets, and this is the pure RMSE value here. So depending on which of the scores you actually are applying here or comparing it, here so the performance remains more or less the same compared to the previous version where we had 6 training units. So what, it gives us, again, quite a strong encouragement to proceed. So we were reducing the training data size by 50%, and the performance level was maintained in this case. So this was the case study for the prognostics, and I would also like to show you how the models actually performed on the detection and the diagnostics case. And here the context is a bit different, and we also compared it to a bit different approaches. But before I start with it, I would like first to introduce how we normally are detecting and diagnosing faults, also in conditions where we don't have access to a lot of different faults to train our algorithm on. So what we typically do is that we train an autoencoder that is trained to reproduce its own input. Then we take the compressed feature space, we feed that into a 1-class classifier, and then we train the 1-class classifier with the target output, and we set it in this case being 1. And this represents for us the distance to the training data. And what we typically try to do is that we train the algorithm either on the first part of our training data. So this is where we assume that our system is still under healthy condition. And then we measure the distance to the training data as it evolves over time. And since we're measuring this distance to the healthy conditions, we could also interpret it as our health indicator. And we set this threshold for this healthy training data based on a validation data set. And we also put a margin or a safety margin that is the gamma here to enable also to adjust the noise that we haven't seen in our training data. So that's how it may look like. So we first train our model on the first part of the observed operating conditions. We set the threshold here based on our validation data set, then we start monitoring. And what this health indicator, or what this distance to our normal data is providing us is also the ability not only to distinguish between healthy and faulty condition, but also to distinguish between different severity levels on our systems. So in this case, we had 2 different levels of the fault, and we could clearly distinguish them in this health indicator. And it was not just a binary classification where we were distinguishing between the healthy and the faulty conditions. And why we were at all using this autoencoder, and the reason is that once we detect something here, we can actually go back to our autoencoder, and then we can check how the residuals of our reconstructed signals look like, and this provides us information on what fault type it may be. Because as already mentioned, so the autoencoder will be trained just on healthy data. So no matter what it actually sees, it will still be mapping it to the healthy condition. So the difference between the input and the reconstructed signal provides us an intuition which of the signals were actually the most impacted. And based on that, we can then deduce which fault patterns it would be, and distinguishing between the different fault types. So it's different fault types will be impacting our signals in different ways, and then we will be able to see then the residuals on different signals, and based on that, we can then distinguish which different fault types may have been occurring. And again, we set the threshold for distinguishing between the impacted and the non-impacted signals based on a validation data set. And based on that, we are then extracting the signals that were the most impacted, assuming that this represents for us the fault signature. So that's just on the basics in order for you to understand what we're actually doing later on. And again, we use the test case of a tryptophan engine. However, in this case, we assume that we would just look into one engine, and this engine would have undergone 20 flight cycles. Now the input data is a bit different. So now we have 175 snapshots of the recordings covering the climb, the cruise, and then the descent conditions. And again, we used here the real flight conditions, and in this case, the fault was the HPC efficiency. However, then with different magnitudes, and we also wanted to evaluate how sensitive the models are to detect for us the different fault types. So obviously, we would be interested to detect it as early as possible. So with a fault magnitude that is as small as possible. So in this case, we applied the similar model that we had before. So we had this the model calibration. We again assume the system model. We again assume that we are measuring the real process parameters here. Then we would calibrate our model and would then feed in the same input to our framework. However, in this case, we are not predicting the remaining useful life. Now we'll be using it to reconstruct our signals. And we wanted also to compare it to something else. And the something else is actually a typical physics-based model that was applied for quite a while, and that's based on the residual detection. So the concept is quite similar to the autoencoders, that we have a system model. We feed in the inputs to the system model. We then estimate the observed parameters. We then compute the difference between the estimated and the observed parameters, and this provides to us this residual, so this delta of each of the signals. And again, depending on how much it would deviate from from zero, basically, we would then detect it as being faulty and then trigger an alarm. So the difference here is that we are using the system model here as well. However, in this case, we're actually using more input or more information from the system models. On the one hand, these virtual parameters, but also the thetas. And then we treat them in quite a similar way. So we take them, those inputs, on the one hand, these deltas, but also the real measurements here, and then we combine this input and train a deep learning diagnostic model. And then again, we do the very same here. However, use the different inputs or a bit different inputs here, and train again a deep learning model. And as already introduced, what we are actually doing is we're using the autoencoder for both approaches. So we're then reconstructing the signal here. We're then using the information from the hidden layer, but then training our 1+ classifier. And we're using the 1+ classifier for fault detection, and we're using the residuals of the reconstructed signal for our fault diagnosis to enable us to distinguish between the different fault types. And that's the output that we actually got. So what we saw on the one hand, or when we compared the different models, so this is the purely data-driven approach. This is where we combine the data-driven information with our operating parameters. This is the residual-based, and this is the hybrid approach, where we combine also the virtual sensors and the thetas. We also compared it, we applied different models to each, so the normal autoencoder, the variation autoencoders, and the 1+ classification support vector machines when we put it on top of the latent input space. And what we saw was that the purely data-driven approach does not perform that well, no matter what we're actually applying. The residual-based performs already quite well, and the hybrid performs, depending on which algorithm we apply, is actually quite similar to the residual-based. But this is for the detection accuracy, and we will see why it still makes sense to apply the hybrid approach, even though it provides a very similar performance as the residual based. However, what we also wanted to evaluate was how does it actually, or why does it not perform that well for the data-driven models? And one of the observations that we made also before, the more variability we see in the input data, the more are the data-driven models struggling with it. And as you saw, we had quite different flight profiles. And so the input data for the purely data-driven models was actually quite diverse. And this was, and this is why, the data-driven models were probably struggling with it. So this is why we also wanted to evaluate how do these models actually behave for those cases where we take out this variability and let the model focus on just purely or on more concise input data. So this is why we only we train two models. So this would be the model where we are above 20K, 10K, and this is where we go to the altitude of above 25K. So in this case, the flight envelopes or the flight profiles would be quite similar, and we would only take those long-range flights. And if we do that, what we see is that the purely data-driven approaches now start performing actually in a quite acceptable way. So we were at around, I think it was, in this case, it's 30 because we also excluded some of the short flights. But now it goes up to 80%. So it's quite an improvement of the performance for the data-driven approaches. So either we extend the training size in order to improve the performance, or we can train dedicated models where we reduce the variability in the data. So this was up to now just on the detection accuracy. However, what we were really interested in was also on fault isolation, so on fault diagnostics. And the question here is, so are we able to distinguish which fault type it would be just by analyzing our residuals? So as you remember, this is not a classification problem. So in the classification problem, we would have already access to different samples of this fault type that we would actually like to detect. But in this case, we did not have these different samples of the fault type. So this is a purely unsupervised fault isolation approach. So we are just trying to isolate the fault based on the residuals of our autoencoder. So if you look into the purely data-driven approach, these were the two signals that were extracted as being the most impacted from the autoencoder, and this is the physical core speed and the static pressure of the HPC outlet. So this already provides at least an indication in which direction where the fault type would be. However, it's still not very precise and would not enable us to pinpoint that. For the residual based, we have on the one hand quite a lot of impacted signals, and here we have a lot of the deltas, and the black ones are those that are really also related to the real fault conditions, but we would also have a bit of a smearing that is appearing here. So we would have three signals that would be detected, but that actually don't have anything to do with the real fault type. And if you look into this hybrid approach, what we see is that it pinpoints to one specific fault, and this is the HPC efficiency modifier, and this is really the root cause of the fault. So it would enable us really to pinpoint exactly to the different fault, to the specific fault type. What I don't show here, we had different levels of fault intensity. And for example, the data-driven approach was only able to detect it or to distinguish it at quite a high intensity level, while the hybrid approach was able for us to pinpoint already at very low fault intensity, so we would have more time to react to the specific fault type. So on the one hand, what we see here that the hybrid approaches are enabling us to pinpoint to the fault type quite specifically, but on the other hand, to detect the fault already with very low fault intensities. For the residual-based, so this can also be considered as a hybrid approach, or one type of the hybrid approach, where we're using the residuals as an input to our model. And in this case, we see quite a lot of smearing that is happening. So we would not, although we were quite good in the detection accuracy, we would not be able to distinguish the fault type very precisely. And for the data-driven, it does not perform that well if we limit the information, or if we limit the diversity of the different fault type, the diversity of the flight conditions, of the operating conditions, we would be able to improve the performance. And if we are able to detect here, so then we are kind of also able to at least to point in the right direction. However, would not be able to distinguish very precisely which of the fault type it would be. So just to wrap up the presentation, so what are the benefits of the hybrid approaches that we saw here? And we saw over the two case studies was that the performance of the prediction really improves. But we can also reduce the training data. So for the prognostics case, we were reducing the training data size by 50%, and this was providing us still the same training accuracy as with the full data size. We could also improve the generalization ability quite significantly, as you remember, particularly for the prognostics case, we had in the testing data set some units that were operated in quite a dissimilar way compared to those in the training data set. And this enables us really to generalize much better also to conditions that were not observed in the training data set. We could also see that it's an improve that the models are able to transfer better between the different units of a fleet. And what we also could see is that we could also improve the interpretability. And this was particularly obvious in the case of the fault isolation. So here, by adding this additional information or additional inputs to our models, we are able then to predict or to distinguish in much a better way what of the fault types are actually underlying these faulty conditions now. And with this, we could really communicate in a better way with the domain expert, explaining also what has been really impacted and what not. So with this, I would like to thank to my team, but also to the different industrial collaborators, and also to the funding agencies who have been quite generously supporting us. And I'm open to your questions if there are any.